will continue our discussion on the velocity analysis problem. We have been looking at the geometric problem in velocity analysis. We have looked at certain concepts of certain geometric concepts like instantaneous center of rotation and relative instantaneous center of rotation, and based on that we have discussed an important theorem which is known as the Aronhold-Kennedy theorem. So, we are going to start by just reviewing the Aronhold-Kennedy theorem, which states that if three bodies are in relative motion with respect to one another, the three relative instantaneous centers of velocity are collinear. So, just to explain this once again, let me consider three bodies. So, 2 and the third one I will define like this, that suppose this is the instantaneous center of rotation of, let me call it body 2. So, this point is the relative instantaneous center of body 2 with the ground, which I call body 1, and let me assume that this is the relative instantaneous center of body 3 with respect to the ground. In other words, these 2 points are hinged to the ground. These 2 points are hinged to the ground at this instant of time. I can consider that these 2 points are hinged to the ground at this point of time. So, as per our nomenclature, we can say that this is I 1 2, this is I 1 3. So, relative instantaneous centers of rotation of body 2 with respect to the ground is I 1 2, relative instantaneous center of rotation of body 3 with respect to the ground is I 1 3. Let me consider this line joining I 1 2 and 1 3. Now, I ask the question, what is the relative instantaneous center of rotation of body 2 and 3? Let me also make one more consideration, that this is omega 2, this is omega 3. I have taken arbitrarily. Now, I ask this question, where lies the relative instantaneous center of rotation of body 2 relative to body 3? Now, as we have seen before, this point may lie outside the domain of the physical domain of the body. This relative instantaneous center of rotation I 2 3 may lie outside the physical domain of the bodies. Let us consider a test point. We will begin with a test point. So, if I consider a test point, let us say G, then I know that velocity of G 2, because this point, remember, this point I can always bring into the extensions of body 2 and body 3. So, G 2 and G 3 are correspondingly points on body 2 and body 3. So, velocity of point G 2, if I mark it with red, it must be perpendicular to this line joining I 1 2 and G. Similarly, the velocity of point G 3 must be perpendicular to this line. So, this is V G 3 and this is V G 2. Now, they do not match. So, definitely G cannot be the relative IC between of 2 and 3. Then we had seen that in order to have a point, a feasible point which can be the relative IC, it must be a point on the line joining I 1 2 and I 1 3. Consider this is our test point now. So, here we have again G 2 and G 3, they are coincident points on the extensions of bodies 2 and 3. Now, once again if I mark by red the velocity of point G 2, it must be perpendicular to this black line. So, V G 2 and velocity of G 3 must also be perpendicular to this black line. Now, their directions match, but their magnitudes do not. Now, how to determine then the exact point? What we do is, since the red vector belongs to body 2. So, from the center of instantaneous center of body 2, I draw this black dashed line, and instantaneous center of body 3, I draw this black line. Wherever they intersect, you can very easily realize you must have velocities as same. These two velocities must be equal. So, here I have V G 2 equal to V G 3. So, this must be the relative IC I 2 3. So, this is I 2 3. Here is I 1 3 and here is I 1 2. And you can see that I 1 2, I 2 3 and I 1 3 lie on a single straight line. Now, here I have fixed the ground, but you can also make the ground move. The situation will not change. The situation will not change even if I let the ground move, because remember I 1 2 is the relative instantaneous center of body 2 with respect to the ground, that will remain the same. I 1 3 is the relative instantaneous center of body 3 with respect to the ground, that also will remain same even if I let the ground move, but keeping the relative motions the same. So, nothing is going to change. So, therefore, we have this theorem known as the Aronhold-Kennedy theorem, which states that if three bodies are in relative motion with respect to one another, the three relative instantaneous centers of velocity are collinear. Now, we are going to look at the implications of this theorem after looking at some examples which you have seen before. So, this is the relative IC between bodies 2 and 3, the revolute pair. For the R pair, the revolute pair itself is the relative IC between 2 3. In the case of a prismatic pair, the relative IC between the bodies 2 and 3 lie on this line which is perpendicular to the direction of sliding. So, this is the sliding direction. And the relative IC lies on this line perpendicular to the sliding direction. So, I 2 3 lies on this red dashed line somewhere at infinity. So, it lies at infinity on this red dashed line. In the case of a purely rolling disk, as you know, it's the velocity of at the point of contact is 0 for pure rolling case. Therefore, this is the relative IC between the ground and the wheel. In the case of rolling with sliding, we cannot exactly locate, but it must lie on this line. Why? Because when it is purely rolling, it must be at the point of contact. When it is purely sliding, when it is only translating and sliding, it must be at infinity, either in the upward or downward direction. So, in between, if it is rolling and sliding, it will lie on this line somewhere. Now, let us apply these concepts in mechanisms. So, we will try to locate the relative ICs for this mechanism. Let me number the links first. So, ground is 1, this is 2, 3 and 4. Now, to locate all the relative ICs, we have what is known as the circle diagram. So, I will mark the number of links. So, 1, 2, 3, 4. So, 1, 2, 3 and 4. So, we have 4 links. So, I will mark 4 points on this circle. I will join the two points if I exactly know the relative IC between those two bodies. So, on the circle, as you realize, I have marked out exactly the number of links I have, and the relative ICs between two links, if it is known, if the relative IC between two links is known, then I will mark that on that circle diagram. I will join. So, for example, I12 is this point, the relative instantaneous center of rotation between 1 and 2 is this ground hinge. So, I know that. So, I will join 1 with 2. I also know the relative instantaneous center of rotation. This is I12, this is I23. I also know that. So, I know I23. This is I34, the relative instantaneous center of rotation of links 3 and 4. So, I know I34. So, I will join 3, 4, and I also know the relative IC of 4, link 4 with respect to link 1. So, I will join 1 and 4. Now, what I do not know, that the circle diagram immediately tells me. For example, I do not know what is the relative IC between 1 and 3. This has not come out as yet, but can we find it? The answer is yes. We need to find out two independent paths starting from 1 or between 1 and 3. Between 1 and 3, we need two independent paths. Why we need it will get cleared very soon. So, one path is I12 and I23. So, I12 and I23. So, I13 must lie on this line as per the Aronhold Kennedy theorem. I13 must lie somewhere on this line, because I12, I23 and I13, these are the 3 relative ICs of 3 bodies 1, 2, 3. So, 3 bodies 1, 2, 3 are in relative motion. So, therefore, their relative ICs must lie on a line. Now, of the 3 relative ICs, I exactly know two of them, I12 and I23. These are known, I12 and I23 are known. So, I13 must lie on this line. So, this is the black line, dashed line. Similarly, 1, 4 and 3, 1 is the ground, 4 and 3, these are 3 bodies again which are in relative motion. So, their relative ICs must lie on a line, of which I14 is known and I 3 4 is known, I 1 4 is here on the ground hinge and I 3 4 is here. So, I 1 3 must also lie on that line. Now, when a point has to lie on both these lines, is the intersection point this, which must be I 1 3. So, I have located now I 1 3. So, I will join it by a solid line. Next is I 2 4. Which is as yet unknown, but then I have two independent paths, I 1 4 and I 1 2. So, I 2 4 must lie on that line. Why? Because 2 1 and 4, the links 2 1 and 4, they are 3 bodies in relative motion. So, the 3 relative ICs must lie on that line, of which I 1 4 and I 1 2 are known to me. So, therefore, I 2 4 must lie on this red dashed line. Similarly, 2 3 4, 2 3 4 are 3 rigid bodies are in relative motion. So, therefore, the 3 relative ICs must lie on that line, of which I 2 3 and I 4 3, I 2 3 and I 4 3 are known to me. So, therefore, I 2 4 must also lie on this line. So, the intersection point gives me I 2 4. So, I have found this as well, and that completes all the relative ICs. So, I have found I 1 3 and I have found I 2 4, which were unknown, using the Kennedy-Aronhold theorem and this circle diagram. Circle diagram helps you to keep track of the bodies of the links and finding out, searching for paths which connect 2 points or 2 links. So, let us proceed further. So, here we have a 3R 1P chain, ground is 1 2 3, the slider is 4. So, again 4 bodies. Now, what do we know? We know I 1 2, we know I 2 3, we know I 3 4, now I 1 4, this is a prismatic pair between links 1 and 4. So, I 1 4 must lie at infinity along this direction, which is perpendicular to the direction of sliding. So, this direction is perpendicular to the direction of sliding. So, I 1 4 must lie at infinity. So, I know this, it is at infinity. Now, let me ask the question whether I can find I, let us say 1 3. So, I have 2 paths, I 1 2, I 1 2 is known and I 2 3 is known. So, therefore, I 1 3 must lie on this line. I 1 3 must lie on this line. The other path I 3 4 is known and I 1 4 is at infinity somewhere. So, therefore, I 1 3 must also lie on this line. The intersection is this. So, this must be I 1 3. So, now I also know I 1 3. Next I ask the question whether I can find out I 2 4. So, I 2 4 must lie on the line of I 1 4 and I 1 2. I 1 4 is at infinity and I 1 2 is this ground hinge, and I 1 4 is at infinity. So, through this point, through this ground hinge, I must draw a line to infinity. So, this line meets this dashed line, this line at infinity. So, these two lines are parallel. So, what I have drawn is a line through I 1 2 to meet I 1 4. Now, I 1 4 is at infinity, and as I have said, I 1 4 lies on this, I 1 4 lies on this line, I 1 4 lies at infinity on this line. Therefore, I must draw a line parallel to that line through I 1 2 to meet at infinity, to meet I 1 4 at infinity. So, that is one. The other path is I 2 3, which is here, I 2 3 and I 3 4, which is here. So, which means it is this line. So, I 2 4 must lie on this line as well. So, this point, as you can see, this point is I 2 4. So, this intersection point is I 2 4. So, now I also know I 2 4. So, I have located all instantaneous centers of rotation. Let us move to the next mechanism. So, let me number 1, 2, 3 and 4. So, there are 4 links. So, 4 points on our circle diagram. I know the IC between 1 and 2. So, I 1 2 is known, I 2 3 is also known, I 1 4 is also known. Now, I 3 4 must lie on this line which is perpendicular to the sliding direction. I 1 4 I 3 4 sorry I 3 4 must lie on this line at infinity, because this is a prismatic pair. So, this also I know is it at it is at infinity. I 3 4 is at infinity on this blue dashed line. Now, I ask this question whether I can find out I 1 3. So, I 1 3 lies on the line of I 1 2, this is I 1 2 and I 2 3. So, which means this line. I 1 3 lies on this red dashed line and I 1 3 also lies on this I 1 4 which is here, and I 4 3 which is at infinity on this line. So, this point, this intersection point must be I 1 3. So, I know I 1 3. Next, I ask the question whether I can locate I 2 4. So, I 2 4 must lie on I 1 2 and I 1 4, I 1 2 and I 1 4 and I 1 2. So, on this line. So, I 1 2 and I 1 4. So, I 2 4 must lie on this black dashed line, and I 2 4 must also lie on I 2 3 and I 3 4. I 2 3 is this, and I 3 4 is at infinity along this blue dashed line, remember. So, therefore, I must draw a line through I 2 3 which is parallel to this blue dashed line. So as to meet I 3 4 at infinity. So, this black dashed line and this blue dashed line, they are parallel. So, where do these two lines meet? They meet here. So, this must be I 2 4. So, we have now located both I 2 4 and I 1 3. So, all the relative ICs are now known. Let us look at this mechanism. Now, this has got 6 links, 1 2 3 4 5 6. So, 6 links. Now, we are going to again see what we know. So, I 1 2 is known, I 2 3 is known here, I 3 4 is known, I 4 1 is known, I 4 5 is known, and I 5 6 is also known. I also know I 3 6. Suppose I want to know I 1 6. So, I am asking this question whether I can find out I 1 6. Now, you will find that there are no two paths between, two independent paths between 1 and 6. So, I must have a path, I define a path as one in which there are 3 rigid bodies, because then only I can apply Aronhold-Kennedy theorem. So, a path with 3 rigid bodies, and I have none. But then if you see, if I can find out I 1 3, then I have one path involving 3 rigid bodies, one will be 1 3 and 3 6. So, let us try to find out 1 3, I 1 3. Now, for I 1 3 I have 2 independent paths involving 2 rigid bodies or 3 rigid bodies. So, one is 1 2, I 1 2 and I 2 3, 1 2 and 2 3. So, this must be one line, and the other path is 1 4 and 4 3, I 1 4 and 4 3. So, this is the other path. So, this point intersection of this is I 1 3. So, I have now located I 1 3. Let me now ask the question whether I can locate I 6 4. In that case, I will have two independent paths involving 3 bodies each on these paths between 1 and 6. Okay. So, I have this question of I 4 6. Now, I 4 6 must lie on I 3 6. So, 3 6 is here and 3 4 is here. So, on this line must lie I 6 4. Similarly, I 6 4 must also lie on I 5 6, which is this, and I 5 4. I 5 4 is this. So, therefore, this intersection point is I 4 6. So, I have located I 4 6. Now, I can ask the question whether I can find out I 1 6. Now, I have two independent paths involving 3 rigid bodies. So, I 4 6 and I 4 1 or 1 4, I 4 6 and I 1 4. So, let me use this. So, here I have this as my path. I passing through I 4 6, which is this, and I 1 4, which is this. So, this line. So, I 1 6 must lie on this line, and I 1 6 must also lie on I 1 3 and I 3 6. I 1 3, this is I 1 3 and I 3 6. I 3 6 is this. So, therefore, it must also lie on this line. Now, I 1 6 therefore, must lie on the intersection of these two black dashed line. Now, these two lines are actually parallel. So, therefore, they meet at infinity. What it means is that body 6 is in pure translation, because the instantaneous center of rotation I 1 6, that means 6 with respect to ground, is at infinity. So, this body 6 is in translation. Body 6 is in translation with respect to the ground, and this mechanism is indeed a parallel transfer device, where body 6 is parallelly transferred. So, it is in pure translation. Let us look at this case of again a six link mechanism. So, 3 4. So, this is a 5 link mechanism. So, 1 is ground, 2 3 4 and 5. On the right also I have another 5 link mechanism, which is only different because of the dimensions. Now, let us look at the relative ICs. So, I know I 1 2, I know I 2 3, I know I 3 4, I know also 3 5, I know 4 1 and I know 5 1. Suppose I want to find out what is I13. Now, there are two sets of independent paths, as you can see. I13 must lie on I12 and I23, I12 and I23, which is this line, and this must also lie on I14 and 43. 14 is this and 43 is this. So, it must lie on this. So, this is the intersection, but then it also must lie on 15 and 53, I15 and I53. So, it meets somewhere. So, it also meets this. Now, these are two independent paths as well, I14, 43 and I15 and 53. So, this also is a possibility for I13. This is also I13, and there will be another I13 that I will obtain using I23 and I12. Now, a single body 3 cannot have 3 relative instantaneous centers of rotation, then it cannot move. And if you remember, the degree of freedom what we had calculated for this mechanism was 0. So, this is not a mechanism, it is actually a structure. Because there are 3 possibilities for relative instantaneous centers of rotation of body 3 with respect to 1, but then the mechanism on the right is actually a mechanism, it has got 1 degree of freedom. On the right, the kinematic chain on the right has 1 degree of freedom because of very special dimensions. And if you again calculate or find out the relative ICs I13, they must lie on these 3 lines as we had done here, and all these lines meet at infinity. All these 3 lines meet at infinity. So, 3 is in translation with respect to the ground. So, in the case of the mechanism on the right, you have motion, because the relative IC of 3, whatever way you calculate, comes at infinity. So, therefore, this can move. Here is the final example. Here I have a chain with 3 links. Now, so this is 2, this is 3, ground is 1. I know I12, I know I13, and in both cases I also know I23. So, this is in pure rolling. So, this is the IC of 2 relative to 3. So, this is in the case here it is I12, this is I13 and this is I23. But then you know this mechanism in which you have 2 friction discs, they can continuously roll. This has 1 degree of freedom, whereas the chain on the right is a structure with 0 degrees of freedom. The reason is very simple. The IC 23 on this gear always remains at this point when these two move, whereas when these two links, if you try to move, this I23 is going to shift out of this line, and once it shifts out of this line, Aronhold-Kennedy theorem does not hold, but it must hold, therefore, this cannot move any further, whereas here the Aronhold-Kennedy theorem is always satisfied. The Aronhold-Kennedy theorem is always satisfied in the case of this 2 friction discs rolling, because I23 always lies on this line. whereas for the kinematic chain on the right, this has a tendency to move out, and that breaks the Aronhold-Kennedy theorem, which must be satisfied. It is a theorem, it must be satisfied. If it is not satisfied, then the thing cannot move. So, that makes the kinematic chain on the right as a structure. So, I will leave you with a summary of what we have discussed today.